Okay, let's summarize what we've seen. For power series, which I will call centered at 0, which will contrast with power series that we'll talk about next, which have a slightly more complicated term that's raised to the nth power. Anyway, for these series right here that we've seen a few examples of, and that you should have read some examples of in the textbook, you would have seen one example that converges only at x equals 0. We did an example where the series converges for all x values, and our very first example was a series that converged for all x between -1 and 1. And so in this case, we say there's a positive number called the radius of convergence, and the series converges whenever the absolute value of x is less than that, and diverges whenever the absolute value of x is greater than r. Okay, so the way you should conceptualize the absolute value of x in this statement is absolute value of x is the distance from x to 0 on the number line. And so that justifies our usage of the term radius. So like a radius of a sphere, a ball would be all x values that, or all points that are within a distance of whatever the radius of the sphere is from the center. It's also why we use the word center right here. So it's like the center of a sphere, and the sphere has radius r. Of course, we're talking just on a number line here. So let's take a look at what that might actually look like on the number line. So if we're talking about a finite radius of convergence right here, the possibilities on the number line are basically look like this. Let's give myself enough room here. Here's our number line, x values. Here would be 0 at the center, and maybe we have like r over here, and then minus r over here. And what we're saying is that on this bit in here, everything in between minus r and r, we have convergence. Convergence for absolute value of x less than r, to say it out properly. And then everywhere outside, which would be everywhere out here and out here, we have divergence. So diverges for absolute value of x greater than r, when the distance to the center, 0, is greater than r. Okay, and it turns out that actually at r and minus r, anything is possible. There are examples of different power series that don't converge at either endpoint, that converge at only the left endpoint, or that converge at only the right endpoint, or that converge at both endpoints. So one thing that we haven't seen an example of is testing for convergence at the endpoints, but as you can imagine, it goes just like our previous arguments. You turn your series, which involves a variable, into a series which involves only fixed numbers, so that the series represents what's going on, say, at r, and then you apply one of your tests to it and determine whether or not it converges. Okay, so remember these new pieces of terminology: radius of convergence and interval of convergence. And there are really only three possibilities. Either r is 0, and so that you only converge at the origin, or r is infinite, essentially, which means you converge for all x, or r is somewhere in between. So power series have a really nice domain. It's always just something that is a distance from the center. And in this case, we would call that 0 right here, the center. Okay.